actual residual like linear dependence of these points as members of R2. Okay? Like we could be talking about 8 points on some 8 points forming some simplex of a some kind of shape in the plane, for instance. It's going to be an 8-dimensional space because we're going to define these as linearly independent objects for the sake of constructing this set of zero chains. In that sense, it's formal. All right, so anyway. So this is probably better illustrated by example, so let's keep going. Let sigma bar be the oriented simplex generated by P0, P1, Pn. So this is oriented n simplex. Note notice the starting at 0 allows the last one to be the number because it has n plus 1. Then the boundary of sigma bar is defined to be the sum j equals 0 to n of -1 to the power j of the oriented simplex formed by deleting the jth vertex here. Where that caret means that that's deleted. All right. So here, this extends linearly to define a mapping from the M chains on K to the what? If you get rid of one, you don't have n plus 1 anymore, you've got n, which means you've got a, well, I should have an n here. Maybe I'm supposed to have an m over there. Whatever. You can use m or n, whatever, right? You ever wonder how to like carefully define the boundary of like a space in Calc 3? This is it. This is the machinery to do it. Like, let's see here, example 8. This is exactly the machine we need to really prove like the generalized Stokes theorem. It's this stuff. Smoothed out, but basically this stuff. Okay, so like if we're talking about the boundary of a 1 simplex, what's that? So for a 1 simplex, we just have what?
It gives us either one or
But we usually just write that P1 minus P0. Because we're talking about the line segment, basically the oriented line segment that starts at 0 and goes to 1, P1, like this, right? The boundary of the line segment, the oriented line segment, is the last point minus the starting point. This is what you want for the fundamental theorem of calculus. You want a difference of the final point minus the initial point. Like, this one, this is, I can't tell you how much I love this stuff. P2, P3, minus P1, oh, my bad. Oh, rats. So the numbering is going to get me into trouble It's not up for grabs, is it? We have to number from 0 if we're going to use this definition, because it matters. Like, you see what I'm saying? I'm not free to label differently, because it messes up my formula. Oh well, but all right. Anyway, so this is, P1, P2 minus P0, P2 plus P0, P1, where I've deleted the 0th one, I deleted the first one, I deleted the second one. How does that comport with the pictures I was drawing a second ago, right? How does that play together? Does it play together with those pictures? Let's rewrite that just a little bit. No. Let's just, I'll redo my pictures. Fair enough. So this is P1, P2, right? Plus P2, P0. Plus P0, P1, right? So if I've got the triangle, right? So P0, P1, P2. See how this works? 1, 2. 2, 0. And P0, P1. It is generating the properly oriented boundary. My bad. So this one is, in our usual right-hand rule stuff, into the page, right? It's generating the clockwise boundary naturally through the algebra of the oriented simplex.
Why did they define it to go the wrong way? We could have just numbered it.
Oh yeah, I mean, the thing is, we don't have to, like, let it be understood that this is, like, we're not going to, let us not forever sentence ourselves to having to number things from 0. Let's understand that, the boundary operator should be defined to go plus, minus, plus, minus. The real issue is how many positions over is the deletion, right? The real formula is we put -1 to the number of transpositions it took to get to the place we're deleting. How many slots over did you have to go? The first one is 0, the second one is 1, and so forth. So check this out. If we were to try this for the tetrahedron, right? Like, what if I do the boundary of, I'll do 1, 2, 3, 4, just to illustrate what I'm talking about, okay? So I'm saying that should be understood. Like, let's go past our naive formula and do what the real idea is, which is we delete the first one, we leave the last alone, we do minus, delete the second one, and we do plus, delete the next one, and we do minus, delete the fourth one, right? And let's see here. It's interesting to change the minuses to pluses to try to understand what's going on here. So if I do, like, P3, P1, P4, P1, P2, P4, and here we'll just, flip the first two. If we look at the simplex, right, and label it however you like, all right? So you guys tell me, how's that going? 2, 3, 4, right? Where's that? 2, 3, 2, then 3, then 4. So that's like this, right? Three, 1, 4. I have difficult. I'm going to look for the 1, 2, 4 one. This one here, right? 1, 2, then 4. See that? If you could envision it, the bottom face here, right down there, 1, 2, 3. How's that going? Where's the 1, 2, 3 one? This one here, right? 2, 2, then 1, then 3. 2, then 1, then 3. So we go. Right? 2, then 1, then 3. So do you see how that's going? Outward orienting on the bottom, outward orienting. If we could go in the back face, the outward pointing normal. It's deriving the outward pointing normal for all the faces automatically by this simple algebra. I get very excited about this. I think it's really cool. I'm easily amused though. So, all right, let's move on here. So, theorem. The boundary squared is 0. So if we do the boundary operator at 2 times, like this, it's 0. So let's see here. Let's try it on example 9, for instance. So if we do, actually let's try it on something easier. Less writing. Yeah, it's right there, why not? I'm about to experience, why not? Boundary of 1, 2, 3, 4. Is oh yeah, wait a minute, what am I doing? Oh my goodness.
Let's not do that, please. We're here for 15 minutes. Just trying to do the calculation.
All right, so let's try this instead. So we've got the sum, let's see here, the boundary of P0 Pn, right? So this is the sum let's see here. So he's like, that's the boundary of, first of all, the sum j equals 1 to n of minus 1 to the j. Delete the jth face, right? But then, since we define this to be linear, we can pull the sum out, you know? We've got the sum j equals 1 to n, and then we're going to have the sum k equals 1 to n of minus 1 to the j minus 1 to the k, and we've got p0 ... We're deleting the kth face, you know? And then somewhere here we're deleting the jth face, right? But this is 0.
Obvious.
Why? Why is it obvious though? Here's why it's obvious. This is symmetric. In J and K, and this is antisymmetric. In J and K. And whenever we sum a symmetric over an antisymmetric tensor, we get 0. This is a general lemma of tensor calculus. Something that I will make people prove in advanced calculus next semester. It's not hard. Basically, you just relabel the sum, use the symmetry here and the antisymmetry here to get back to minus what you started with. And since we're not working over a field of characteristic 2, once you have twice something is equal to 0, it makes it 0. So let it be understood, we're not working. We're in the reals. We're keeping it real. So anyway, that brings us to section 5.2, which is on homology. So next time we're going to see how we can exploit the linear algebra of the boundary operator to expose the shape of holes in these space and to calculate what are called Betti numbers. And hopefully we'll also see how this connects to like the Euler characteristic and things. So yeah, the Euler, excuse me, the Euler characteristic, that's better. Thank you. Thank you, Preston.